in the generalization in mind and machine project at the University of Bristol. So as we've already seen, adversarial examples or images are stimuli specifically modified to fool neural networks, and they've become very popular in research and very important in research, basically for obvious reasons, right? Security issues, the robustness of neural networks, etc. So we can see this stop sign with adversarial patches on it. It's actually designed to fool a neural network into classifying it as a 45 mile per hour speed limit sign rather than a stop sign. And recently, the adversarial examples have also been used as arguments against statements of similarity between human vision and specifically convolutional neural networks. So this is a classical example where a panda gets classified as a gibbon after the adversarial noise has been added. And the claim is that, well, to humans, these perturbations are imperceptible, and neural networks become totally inaccurate in classification. Other attacks include single pixel attacks, where you change the value of a single pixel, it becomes diagnostic in classification, and the neural network fails spectacularly. So this has been an argument to say, well, humans obviously do something different than neural networks. But very recently, there have been quite a few researchers stating the opposite, that we can use adversarial examples to point out the similarities between human vision and convolutional neural networks. For example, Zhu and Firestone have stated that the failure of neural networks and the imperceptibility of these attacks for humans doesn't imply differences in computation or in classification. Rather, it's a reflection of human vision, of the restrictions and constraints of human vision, and that we should actually use modifications and perturbances which are clearly perceptible to both mind and machine, to both people and to neural networks. So in this example, this is an image which was generated by evolutionary algorithms to match the baseball class and to be classified as a baseball by neural networks. So they conducted a large study with some experiments, and in one of those experiments they used images like these, and they report these results. So 90% of the participants agree with the neural network classification at above chance levels, and for all the images they've used, out of those, 81% of the images show above chance levels of agreement. So we saw this result when the paper was first published on arXiv, and it seemed kind of really definitive, a strong statement, and they conclude that there's large overlap between what humans do and what networks do, and obviously humans kind of looked at the same features and used the same features to classify these kinds of images as do neural networks. Well, since then, the paper has been published in Nature Communications, and the data has become publicly available. So what wasn't reported for this specific experiment was that the actual average level of agreement was rather low, so under 10%, or the average participant was agreeing with the neural networks on only close to 5 out of the 48 images, and that for this specific image, the agreement was only 3.45%. So there have been other papers which have made these kind of strong claims. People are susceptible to adversarial attacks and accuracy falls, just like with neural networks. And we've started a series of experiments to test this behaviorally in more of a psychological tradition. I come here as a cognitive psychologist, a novice to machine learning. So I'm going to present one of these experiments. So we chose stimuli which actually they chose in their experiment, and that's from a different paper. 3 experimental conditions. We've labeled them kind of basically half on what they look like and half how they were generated. So what we label as regular images were made by evolutionary algorithms to match classes in ImageNet. The irregular ones, and they're called regular ones because they kind of form these symmetries and shapes which kind of look regular. The irregular ones look like noise, kind of, and they're done by different encoding in the same evolutionary algorithms. And you can kind of see a shape or a pattern in the middle. This particular image was labeled as a centipede, and you can kind of see it if you have a limited number of labels. You might choose centipede. And the final one is actually a set of irregular images which were, through the evolutionary algorithm, encoded to match MNIST digits. So this particular image was classified by neural networks which were trained on MNIST to be classified as a digit 3, right? So the participants went through the same single trial procedure for all 3 conditions. An image was shown and 10 labels below it. The image was shown for a maximum of 10 seconds, then it would become invisible. But the participants could make their choice at any time. And since I come from a meta-reasoning background, kind of, we put in just that after every choice they made, they would also make a confidence judgment from on a scale from 0 to 100%, so we can just see how confident they are in their decision, not just the raw classification output they give. So what we expected was rather different than what these previous papers claim, like large overlap and systematic effects. We expected that the results would be quite different depending on the experimental condition, and we expected large variability within each condition. So to have images which would be generated by the same process, but that neural networks and humans don't actually look at the same features. So first off, we have the level of agreement between neural networks and humans, and we can see that not a single condition goes above 30% of average agreement. And the MNIST digits are above chance, but just barely above chance. All of the pairwise comparisons are highly significant, as well as the main effect, obviously. Then when we look within each condition, for example, the regular images, we see this image, which has been classified by the neural network as a computer keyboard, and by nearly 60% of our participants as a computer keyboard, and you can see kind of the features which, if you have labels which aren't similar, like typing machines or something like that, participants will probably choose computer keyboard. On the other hand, we have an image which was made by the same algorithm, by the same type of encoding to match king penguin, and below chance levels or below chance numbers of our participants chose the correct classification, or the classification the neural network chose. And there's a wide kind of a margin, and we see that in all of the images we used. For some, the accuracy is quite above chance, and for some, it's even below chance, because people tend to latch on completely different features than the neural networks, and then they choose a completely different label at above chance levels, which has nothing to do with the classification the neural networks made. For the irregular ones, we see a similar pattern. So above 50% for the centipede, but for the lesser panda, only just about 2%. So these images show the same thing. The average level of agreement was about 20%, but there was a large kind of range, a large variability within the condition itself. And finally, the MNIST ones, these were indirectly coded, so they kind of have shapes. So we've seen kind of a lot of zeros. People tend to choose a lot of zeros, a lot of 8s when they see some circular kind of shapes or something, or when they perceive that there's nothing on the image, then they choose 0. That kind of makes some sense, but for other images we see well below chance, and on average it's at about chance. Sometimes they're above chance for these specific indirectly coded images. When it comes to the confidence levels, well, we again found a main effect, which was due to the differences between the MNIST kind of digits and the rest of them. And what I would really like to highlight here is that the average confidence for humans doesn't go above like 42.5%, while neural networks gave kind of a confidence rating of above 99% for all of these images when they classified them after training on ImageNet and on MNIST. So there's a few problems we would like to highlight in our conclusions. First, the level of agreement highly depends on the experimental design you choose to use in your experiments with humans. It can depend on the instruction you give, on the labels people have at their disposal, on how you present your images. People are, compared to machines, people are very, very messy. So we see messy results, and sometimes people get large kind of overlaps and make large, bold statements without actually looking at the total kind of data and looking at the errors and looking at the variability and specific images, etc. Also, the process by which the images are generated, of course, makes a difference. So for some adversarial examples, you're never going to get overlap. For some, you're going to get some overlap. But again, we haven't found a systematic effect, which was claimed by that paper as an example and by other papers. So it's difficult to say that, or it's unfounded to say that convolutional neural networks and human vision do qualitatively the same thing. But if this discussion is going to tell us something more, if we are going to learn something about human vision and perhaps more about what the neural networks are representing and doing, we're going to need to introduce some nuance and refine our experimentation, especially behavioral stuff, because, as I said, humans are quite messy. That's it.